Good day, class. So we will now be continuing in this slide on the application of Kremser equation in determining the theoretical number of stages for a liquid-liquid extraction process. So this time I have already selected a sample problem in the book. That way, all my numerical data will be in agreement and can be processed. So in this problem, you are given an inlet water solution of 100 kilogram per hour containing 0.010 weight fraction nicotine in water, which is stripped with a kerosene stream of 200 kilogram per hour containing 0.0005 weight fraction nicotine in a countercurrent stage uh, tower. Now you have to understand, class, that though stripping was the term that is used here, you are processing two liquid streams or two liquid phases. And the feed, which contains the nicotine, will be processed by stripping it off with nicotine using the kerosene stream that also contains a little of nicotine. So in this case, your water solution, which is the feed, composed of course of nicotine and water, will be your feed, and your solvent in this case will be your kerosene containing a little of nicotine as your solvent. Though again the word that is being used is strip, the stripping process here is comparable to liquid-liquid extraction. Now, the water and kerosene are essentially immiscible in each other, and as such, it gives us assurance that the product streams will also be immiscible. Now, it is desired to reduce the concentration of the exit water to 0.0010 weight fraction nicotine. Now, determine the theoretical number of stages needed using the equilibrium data here below, which also gives us the fraction of nicotine in water solution in X and that in Y. Okay, so X is the weight fraction of nicotine in water solution and Y is the weight fraction of nicotine in the kerosene solution. Okay, so this would be like saying that this particular concentration of nicotine in the water solution is in equilibrium with this concentration of nicotine in the kerosene solution or in our solvent, and so on and so forth with the following pairs of data. So let's write down our solution or start our solution for this problem. So we always start with the given. So for this problem, we're given LO as the feed in the amount of 100 kilograms per hour aqueous solution of nicotine. Now, the weight fraction of nicotine in the feed is 0.010. And then this feed is to be processed by the solvent, which is kerosene with nicotine in the amount of 200 kilograms per hour. And it's not pure this time, but it has a little of nicotine. So we have B sub n plus 1. So this is Y sub n plus 1. And the nicotine that we have in our solvent is 0.0005. Now, it is expected that we will decrease the concentration of nicotine in the water solution, and that's referring to our raffinate, in the amount of 0.0010. Okay, so in this particular set of given information, we are required to determine the theoretical number of stages. Now, of course, the equilibrium data has to go with this particular set of information. Now, in determining the theoretical number of steps, we can use the Kremser equation and we can use the graphical approach, but our focus in this particular example is in the use of the Kremser equation. So we will write down the Kremser equation this time. So in this equation, we have ln in both the numerator and the denominator. And our numerator has, so if you're going to work on the representations that we have started here on the given, so our Kremser equation would be ln of xao minus yn plus 1 over m all over. So this would be xn minus y sub n plus 1 over m. This will be multiplied to 1 over a, quantity 1 plus a rather, minus a plus a. Okay, so this is our Kremser equation. Now, in terms of what we have already, so let's check what we have already. We have XAO, we have YAN, and we have XAN. So that leaves us, this will be our first equation, that leaves us with the absorption factor to determine. That way, we will determine the theoretical number of stages. Now, take note also that in this absorption factor, there's a need for us to get the geometric mean of the absorption factor for both the dilute end and the concentration end of our tower or our column. Now, whichever of the two is lesser in value, that would then be the slope that we will use here for the m, because the m here will be the slope of the dilute end of the column. So that would be the lesser amount of the two. So now let's go to determining the absorption factor. So we will have, let's say, 0.1. Now, 0.1, if we have the McCabe orientation of labeling our tower, 0.1 is at the bottom. And the bottom part of the tower is the dilute end. So at the bottom part, we have the raffinate and we have the solvent. So the raffinate and the solvent at the bottom. So if we will have this represented as, let me change font color. So if we will have it labeled as A1, the bottom part of our tower, then we will be needing the Ln, the M1, and the V sub n plus 1. Okay, this would be the streams that are in the bottom part of the tower, and this is the corresponding slope of the tower. Now, what do we have so far? So far, what we know is just the B sub n plus 1. We don't know these two. Okay, so we'll just label this as equation 2. Now, for the concentrated end of the tower, and that's 0.2 in the representation of McCabe, which also Janku please use at times, we have a 2. So we'll find the absorption factor at the concentrated end of the tower, the A2. And in here, of course, we'll be using LO, the feed will be determining the slope at the concentrated end, and we will have here the extract, which is V1. Now, of the three things that we have written in the formula, so far, what we know is just the LO. So that leaves us with 1, 2, 3, 4 to determine, unknowns to determine. So this will be our equation 3. Now, if we would like to find the Ln and the V1, that could be easily determined using what we call as the material balance. So you can have overall material balance and you can have component balance. And that we do, and then we go for the slopes. So let's have another slide and we will use material balance. So if you use overall material balance, that would be LO plus V sub n plus 1 being equal to Ln plus V1. Okay? And this is, of course, equal to the bulk phase M. Now, our LO in this case is 100. And our V sub n plus 1 is 200. The Ln and the V1, we do not know. but the M is known to be the sum of the two, which is, of course, 300. Now we have 300 is equal to ln plus V1 equal to M. Okay, now my goal is I will find the ln and the V1. If we will try, for example, using component balance, let's say on A, and we will work with the information that we already know, we can use LO, XAO, plus V, N plus 1, Y, A, N plus 1. That's your V sub N plus 1. And this is M, X, A, M. This particular value will not change whatever the streams that I am accounting for the A. So I will start with this, that way I can find the XAM. So in this case, yes, the XAM. So I have here LO 100. The XAO is 0.010. The V sub n plus 1 is 200, and your Y sub a n plus 1 is 0.0005. Now, I will have the M, which is 300, and the XAM. Both of these will not be changing whatever I equate them to in here. So there's no need for you to individually determine XAM or M for that matter. Now, the product of these two will be equivalent to, this is 1.1. And this can be equated to a different set. What I mean different set, so this could be equated to ln xan plus v1 ya1. Okay? Now, we have 1.1 is equal to, we do not know ln, but it could be expressed in terms of v1, in the same thing that we don't know v1, but it could be expressed in terms of ln. So if we will have ln expressed in terms of v1, I will have something like 300 minus v1, and your xan is known to have a value of, so it's given in the problem to have a value of 0.001. Okay, 2 zeros. And your V1, of course, is V1, but YA1 is unknown. Okay, we do not know YA1. So in here, you have 1.1 being equal to, so we'll have 300 times 0.001. That would be 0.3. And you have this V1 minus here, so 1 minus 0.001. So that would be 0.999. Nonetheless, by the way, class, we cannot use or we cannot combine this to V1 because this one has an unknown YA1. So we cannot combine the two. So that would mean that you have here minus 0.001 V1 plus YA1 V1. Now, I really intended to present it in this manner. That way, you will know what an alternative route in the solution will you work for. So this is already our equation for knowing that if you do component balance, you will have, or you will remain with two unknowns V1 and YA1. I mentioned also throughout our discussion that whenever you do material balances, if you do another component balance, the solution will still not find the values that you're looking for because you're supposed to only to deal with two material balance equation, one overall material balance and one component balance. So in this case, you should have another equation to use. That way, you'll be able to find the unknowns that we're looking for. And that equation is using the inert amount of streams. So if you recall, in gas absorption and stripping, we're also allowed to use V primes and L primes, the inert amount of streams or phases that are given in a particular separation problem. So in this case, we will do that. So we'll have another sheet here, and we will use the L prime and, shall I say, V prime route in the solution. So let's say we'll find L prime, the inert amount of the feed that we have processed. So if our feed is 100 and it contains 0.010 weight percent nicotine, so our L prime would be 100 times the quantity 1 minus 0.010. This will give you an answer which is 99. This 99 is kilogram water, the inert part of your feed per hour. You can do the same with that of the solvent, which is your kerosene. Your solvent is 200 and it's containing 0.0005 nicotine. So then the kerosene would be 200 times the quantity 1 minus 0.0005. And that would be your kerosene only. So in this case, you will have 199.9 kilogram kerosene per hour. Now, you know already the inert streams. You know already the inert streams. Now, of these two, we know that the amount of water that entered in the feed would be the same amount of water that is present in the raffinate. And good, because in the raffinate, we are provided. So we are provided with the concentration of, in this case, nicotine. So in the raffinate, so I'll say here, but Ln has already the amount of 0.001 weight fraction nicotine. So your Ln, if I will multiply that with 1 minus xan, the nicotine that it contains, it should be the same L prime that we have in here, because this one represents already the water that is present in the raffinate. In this process, I can find the Ln. So Ln is equal to L prime all over 1 minus xan. Your L prime is 99. 1 minus 0.001. Let me check. Correct. For the nicotine and raffinate, this will give you an Ln value of 99.10 kilogram per hour. Now remember, let's go back to our slide, the previous slide. Remember that I have represented here Ln, the Ln to be 300 minus V1. Okay, the Ln is 300 minus V1. So it follows that V1 is 300 minus Ln. And the V1 that remained unknown in equation 4 can now be solved. So 300 minus 99.1 will be 200.9. So kilogram per hour. This V1 that we got here, we now can substitute in here to find the YA1. So if we do that, we will have 1.1 equal to 0.3 minus 0.001 times the V1 of 200.9 plus YA1, which we do not know, times the 200.9. In here, you'll be able to find the YA1. Let's find the value of YA1. The value of your YA1 would be 0.00498. So in the process now, we have determined the YA1. In the other slide, we have determined the Ln and the V1. Now, if we go back to our first slide, the Ln and the V1 now are already known quantities. That leaves us with the M1 and the M2. Now, let me discuss about how to find the slope M1 and M2. For M1, you need to find, or you need to use the YA, in that case, YA1, in our representation. So for M1, since it is our, let me check, that's our dilute end. Yes, this is our dilute. No, this is, yes, the dilute end, because we have the raffinate and the, shall I say, the solvent that is being used here. So for your M1, you can find the corresponding X. So you will find the corresponding X in the plotted equilibrium data that is provided by the problem. So you are to plot and find the equilibrium data. But the question is, what YA1 will you use? What particular YA1 will you use? That will be the YA1, or what will be the Y that you will use, that will be the YA1 that we solved a while ago. So the YA1 that we solved is this, 0.00498. Okay, so this is your 0.00498. This is, I'll use a different color. This will be the concentration that you will look for the Y of in the equilibrium data that is provided. If you have plotted, as I mentioned just a few seconds ago, if you have plotted the X and Y data in the form of a curve or a line, it's still okay, but that would take time. But you can directly find and approximate a very near value to the slope without having to plot the XY pair of data from the raw data themselves. So for the 0.00498, if we go back to our slide, 0.00498, it's comparable to this. I'd like to, it's 0.498 for the Y. So it's like, if I will annotate class, that data will be this. And the corresponding value of the X in equilibrium with it would be this one. Okay? So you just look for the approximate. So if you really want the 0.00498, you can approximate by interpolating between, in that case, 0.004, between these two values, 0.006 na siya. This one is 0.002. 0.0058 is between these two and this. So you can interpolate between these two data. But nonetheless, we will not interpret anymore because we know for one that this is not a straight line that we're talking about. So we will just approximate by directly using the X value for the Y, which means that this is the equilibrated concentration of the raffinate for this corresponding extract layer, for example. So this is your extract layer and this is your corresponding raffinate layer composition in equilibrium with it. It need not be, for example, an extract and raffinate, because we know extract is already the last part and raffinate is also the last part. But what I mean is, like, this is the equilibrium concentration for this equilibrium concentration in the, shall I say, the solvent-rich layer, and this one for the water-rich layer, because we cannot use extract and raffinate because the two is already referring to the last streams. the end streams for our multi-stage process. So if we will use this as the corresponding x for the y, which is 0.00498, we'll go back to our solution. You will get, so I will place here, so that was 0.005, a crude equivalent to the 0.0045 there. Ours is 0.0049. You will be able to get an M value here, which is just the pure ratio of the two. And you have the X corresponding to this YA1. That 0.00498 divided by 0.005 will give you a 0.996. A 0.996. It's very crude, of course. It's very crude. But if you want to interpolate, then you can. If you interpolate, let's see which value we will be, what value we'll be getting, and how far will it be from the real answer, which was done using graphical approach. So if we will interpolate using two sets of data, I'll use this one, the one that we have in the graph. Okay, you will be using these two pairs against these two pairs, and the 0.00498 will be in between the two. Okay, so we'll go back to our whiteboard, and let's say if we interpolate. So I'll place here the X and the Y values. So the one that we used is this one. We use 0.005 for the 0.00498. So let's say we will interpolate and see which one will give us much nearer value to the value of the theoretical number of stages determined graphically. Okay, so I will have the 0.00454, you have 0.00498, and you have 0.00682. This one is what we're after. So for the 0.00454, we have 0.005, and in here we have 0.00746. So if we will interpolate, what would be the corresponding X that we can replace with this one? Okay, so let's check. So we have 0.005 minus X divided by 0.005 minus 0.00746 equated to 0.00454 minus 0.00498 all over 0.00454 minus 0.00682. Let's see what would be the value of X that we will be getting out of this. The X that you will be getting if you have interpolated would be 0.00453. In this part, you will be getting an M value then. So your corresponding M for this would be the YA1 that we have, which is 0.00498 divided by 0.00453, which is 1.1. If you're going to check, class, I think there's something wrong with the value that I got here. I will recheck. Wait a minute. If the x that I got here corresponding to this value of 0.00498 is acceptable, because this one is not in between these two. So I have to recheck, because the value that I should be getting should be between 0.005 and 0.00746. Let me check, class. This one is not correct. So if we were going to process the interpolation that we did, the value should be, so let me erase. Same thing, this would be affected, of course. Just arrange all of this. So the x value should be 0.00547. 0.005475. The corresponding m that we will be getting, so I will have here, your y is, in this case, the y that we have is 0.004498. If you'll use this one, that's 0.005475. The m will be 0.91. Now look at the very crude answer that we got. So if we use the x value of 0.005, which is for the y, which is 0.00454, this is our slope. Whereas if we interpolated, we expect a value in between these two, this will be the slope that we are getting. So that's the importance rather of having to find the more or less the near approximate value for the equilibrium data, not by rounding off the raw data, but rather really dealing with the pair of data that are provided, even though we know that if plotted, we will not have a straight line. So of the two slopes that we will have here, we will use the slope of 0.99, not the 0.96. Okay, so we will use this one. So I will use a different one here. We will use the 0.91 slope. This 0.91 that we have here will be the slope that we will be using in here. So this would be the M1 that we'll be using the YA1 that we got will be used, which of the two will be using the YA1? Remember that the YA1 of 0.00498 corresponds to the concentration in the extract, the concentration of the extract. In our representation here, which of the two is the slope, which will be using the concentration of the extract? This is the extract, right? Based on the representation that we're using in John Copley. So then this would be the M that we're looking for. So I will write here M2 then would be equal to 0.91. So this will be now a check. Okay, your M2. Again, we will use M2 as equal to 0.91 because the equilibrium concentration that we based it on is that of the extract. It is the extract where we base its concentration. Okay, now we go now in here. In terms of the equilibrium concentration that we can use, that would be that of the raffinate, the Ln. And the problem already gave us the Ln. So let me go back to the slide where I can write for the M2. So although I wrote here M1, this M1 corresponding to our representation in the John Copley's way, this M1 is actually M2. So I will change this to M2. Now we look for M1. So we'll go to the next slide. For M1, funny, looks funny. For M1, we will use the XAN, the raffinate concentration. The raffinate concentration is 0.001. We check if we have more or less this value in the data that we have. So we go back to our slide, the 0.001. I think you could see that we have it here now. So I think we will not need to interpolate because more or less this is already 0.001. This is the y corresponding to it, the 0.000806. Okay, so we will right now go back to our solution. Your y for this is 0.000806. So if we will solve for the M1, that would be 0.000806 divided by 0.001. Okay, 0.00806 divided by 0.001. That would give us 0.000806 divided by 0.001. That would give us 0.806 as the slope. And this is the slope that we will be using in here. So your M1 is 0.0 or 0.806. Now, with all the values that we got, we can now determine the A1 and the A2. Now, with the M's that we have, and then solve for the geometric mean of the two. So let's go here. So A1 is equal to ln over M1 B sub n plus 1. So the value that we got for the ln is 99.10. The M1 that we got is 0.806. Let me check if I recalled it right. So 0.806. Here we have it. And then we have the V sub n plus 1, which is 200. So now we have the A1. So the 99.10 divided by 0.806 divided by 200 will give us a 0.6147. We do the same for A2. We substitute the value. So we have LO, M2, V1. So for our LO, we have 100. For the M2, we have 0.91. Let me check if I have recalled it right. 91, right? And for the V1, 200.9. So this is 200.9. So we have 100 divided by 0.91. Then we divide it further by 200.9. That would be 0.54699. Now, if you get the geometric mean of the two, that would be 0.5799 again. Okay? Now, of the two, of the 0.806 and the 0.91, we will use the 0.806 for the M because it is lesser of the two. Okay? 0.00, 0.806. Okay, this one is lesser. So we go now to determining the number of stages. So from equation 1, n is equal to, so we have the ln, xao is 0.010, xn is 0.0010, then we have ya1, forgot the ya1, 0.00498. By the way, it's not, this is yn plus 1, sorry. So that should be 0.005, okay? Divided by the m, the lesser of the two, minus 0.0005 divided by 0.806. Then we will multiply it with the geometric mean, 5799. 1 minus 5799 plus 0.5799 based on formula. Then this is ln of 1 over 0.5799. So let us find the answer. So let's compute first and see if it's comparable to if we do the graphical approach. Now, if you will process everything in this formula, the theoretical number of stages is 4.394. Now, if we do it graphically, and you can check on the example in the textbook when the process is done graphically. So using graphical approach, the value for n theoretical, this one is, by the way, also n theoretical, is 4.5. Okay. This one is also crude in the sense that we determine the slopes using the raw approximated equilibrium pair of data. We did not plot. This one we say can be accurate because we have plotted, but nonetheless, the way we have drawn the curve for the equilibrium pairs of x and y will not be as accurate in itself as well. So it's always for the user to choose which do you think in your judgment is the best answer. But nonetheless, if you look at it, the two values almost are the same. So they more or less agree with each other. But as to the accuracy, this one has certain limitation because we have approximated also. This one, the graphical approach, may have less accuracy based on the manner of the plotting, the reading of the values, and the stepping off that happened during the process of determining the number of steps. So this is how we determine the number of stages using Kremser equation. Now, the remaining topic on the minimum solvent requirement, which is connected to the optimum solvent requirement, and the use of the extraction factor will be discussed on our next meeting. Anyway, they are short topic class. So hopefully you've learned something new for this particular recording. Bye for now.